We'll start off with finite-state automata via a simple example. This is an example finite-state automaton. To understand what's going on here, we have two things that are called states, and these things are called transitions or arcs. And intuitively, one of the states is a start state, Q0, we'll call it, and there's another state which is a accepting state or a final state, Q1. And intuitively, the way this works, an automaton is a device for accepting or rejecting strings, and you start at the start state, at the start of the string, and you look at what's next in the string, and if you get something that has an arc outgoing from the state either you're in that's labeled with the next thing in the string, then you can follow that arc and consume the thing in the string. So intuitively, you start at Q0, the start state. If A is the first thing in your string, then you can go to Q1, and if the next thing in your string is B, for example, you can take this transition to Q1 again, and if you end up in Q1 at the end of the string, then whatever the string was would be accepted. So this automaton, for example, accepts all and only those strings that begin with A and then have nothing but B in them. More precisely, it accepts all and only the strings that are accepted by the regular expression AB star. So it has to have exactly one instance of A at the beginning to get out of Q0 into Q1, and then it can have 0 or more instances of B, no matter how many it is. It will continue to loop and stay in Q1, and at the end of the string, if you're in Q1, then you are accepted because you're in a final state. So let me give a formal full definition to buttress that intuition. A finite state automaton consists of the following. First, there's a finite set of states, Q, and we'll arbitrarily label them Q0 through n-1 if they're n states, and arbitrarily, as convention, Q0 is what we call the start state. There's a finite input alphabet, sigma, capital sigma, of symbols that are the symbols that comprise strings. This is the same kind of sigma that you see in the constitution of regular expressions. Some subset of the states is a set of final. That set of final states is F, subset of Q. It might be none, it might be all, it might be some but not all. And then there's a transition relation, delta, that is comprised of a finite set of transitions, each of which has the form, you're in state Q, you get input symbol I, and you go to state Q prime. So I is either a symbol in the input alphabet sigma, or it is the empty string epsilon. And informally, this statement of the transition is that if you're in state Q and have input I available next, you can consume it and move to state Q prime. So I'll give you here, we had our example automaton, once again in the bottom left, an equivalent specification of that formally through the devices that I've got, through the components that I've got up above, is as follows in the bottom right. So the set of states Q is Q0 and Q1. The input alphabet will take to be the symbols A and B. The set of final states is simply the set Q1. And the transition relation has two elements in it. One is a relation between Q0 and Q1 with the input symbol A, and the other is a transition between Q1 and itself with the input symbol B. With an FSA, we can talk about now an acceptance criterion, and this is slightly informal, but it's still faithful to the formal definition. An FSA accepts a string if and only if you can recursively apply the transition relation to the current state, where we initialize at state Q0, the start state, and the current position in the string, which is initialized to the beginning of the string, and you can get to a final state with the string being completely consumed. We could say that if the sequence of transitions is of length n, we might depict a path through the automaton that accepts the string W as the following. It's just a sequence of these transitions, so we're going to label the transitions that way. And now Q star, where you end up, has to be a final state, and the i's have to be appropriately sequenced inputs from the string W. So here's an illustration of how to do acceptance determination or rejection determination. Let's start with this. This is a slightly different automaton. It looks the same as before, except now it has an additional arc that goes from Q1 to Q0 with the label A. So if you're in state Q1 and you see A, then you can transition back to Q0. And here we have three separate strings, and at every point in the we'll sort of denote the position of the string during consideration of the string and the automaton together with this vertical line. So let's take the first string, which is ABB. So we start off, we're in Q0, the start state, and we're in the beginning of the string. The next thing in the string is A, and so we have an outgoing state from Q0 to Q1, A, labeled A, and so we can take it. We move forward in the string, and we're now in state Q1. The next thing now is the symbol B. We have an outgoing arc from Q1, which is labeled B. That's the loop arc, and so we can consume B, and we actually wind up in the same state Q1 again because B was a loop arc in this case. Once again, we have B in the end, and the B is the next symbol. We consume it again, use the loop arc, and now we're at the end of the string, and we're in Q1, and Q1 is a final state, so we say that this string is accepted because there was a sequence of applications of the transition relation that got us from the start state to a final state, and we were at the end of the string. Example 2, the string B. Here we're in the start state Q0, and the next thing ahead of us is B. There's no outgoing transition from Q0 that has a label B. So immediately this string is rejected. That's string number 2. String number 3, we start in Q0, we're at A, so we can consume A, move to Q1. Now we have B, we can consume B, we stay in Q1. We have A next. Now we can't say we've accepted anything even though we're in a final state because we're not done with the string. What's next is A. We have a transition out of Q1, which is labeled A, and so we take it, we go back to Q0. Now we're at the end of the string, and we're not in a final state. So although we got to the end of the string, we're not in a final state, so we reject this string as well. So this is a set of examples of the application of the acceptance criterion. Now, importantly, it turns out that for every regular expression, to bring this back to regular expressions, there is a finite state automaton that accepts all and only the strings that the regex matches. And the same is true vice versa. For every finite state automaton, there is a regex that matches all and only the strings that the automaton accepts. And so actually there's a formal equivalence between the two things. Okay, now I elided over this at the beginning, but there's actually a distinction which is important between deterministic and non-deterministic finite state automata. In a deterministic finite state automaton, each transition's input symbol must be a symbol in the alphabet. It cannot be the empty string epsilon. Second, the transition relation is a function. So there can be only one state that you wind up into for any given current state input symbol pair. So these things together mean that in a deterministic finite state automaton, there is never more than one transition possible given a state and the current position in the string. So the examples that I showed you already of a finite state automata are deterministic. There are also non-deterministic finite state automata. In these cases, neither of the above two constraints hold. So here are a couple example deterministic and equivalent non-deterministic finite state automata. We have a deterministic automaton on the left and a non-deterministic on the right. The non-deterministic finite state automaton is non-deterministic because it has a transition in it, which is labeled with the empty string. And what that means is that you don't actually have to consume an input from the string to actually take that transition. So intuitively, this automaton will accept either the string ABC followed by any number of Ds, or the string nothing, just BC followed by any number of Ds. And you can see equivalently that the deterministic automaton does the same thing. So it can take A, B, C, and then any number of Ds, or just B, C, and any number of Ds. And you can see here that these drawings that I'm giving are basically, those are what are called paths through the automaton in the previous slide. And this idea of a path through an automaton is a useful way of talking about the relations between strings and automata. Here's another equivalent deterministic, non-deterministic pair. In this case, it's the fact that there are two transitions out of the same state that have the same label that makes the latter automaton non-deterministic. That is not true in the upper automaton. In the upper automaton, there's only one transition, outgoing transition from each state with any given label, and there's also no epsilon transitions. So you can see intuitively, if we just you can eyeball the set of strings that this automaton will accept. You can see that it would accept cab, it would accept cabin, or it would accept tin. And you can see, let's take a look at the top automaton, the bottom automaton. It would accept cab, it would accept cabin, and it would accept 10. So they accept and reject the same strings. Now, checking for acceptance is harder for non-deterministic than for deterministic finite-state automata due to the existence of these choice points. So the simple story that I showed you before is not going to hold as straightforwardly because there's more than one thing that we can do. So in this automaton, for example, if you're in Q5 and the next thing you have is a B, then I could either take this transition or I could take this transition. And so there's a little more machinery that I need. So I can deal with this. There are methods for dealing with this, and there are a few algorithmic options for how to do string acceptance rejection checks in non-deterministic automata. There's backup, which basically involves marking choice points and going back to an earlier choice point if I failed in pursuing one choice after a choice point. There's look ahead, which is to look ahead farther in the string for guidance about maybe which path I ought to choose. And then there's parallelism, where what I maintain for every position in the string is not which state I'm in, but it's what set of states can I be in. And those are all different options. I'm not going to cover them in greater detail, but in the readings and other resources, you can look at algorithmic methods for checking string acceptance and rejection in a non-deterministic automaton. Now, every non-deterministic automaton can actually be determinized to create an equivalent DFSA that accepts and rejects the same string. So the two methods are expressively equivalent. There's no difference in terms of what we're getting, what string sets we can define as accepted or rejected. Also, you will sometimes find a distinction between total and partial finite-state automata. In a total automaton, for every state Q and every input symbol in the alphabet sigma, there is some transition out of Q that is labeled with that input symbol. It may go to any other state or may stay in the same state, but there is such a transition. Graphically, we can visualize this that in every state, for every symbol in sigma, there's at least one outgoing arc labeled with that symbol. And if an FSA is not total, then it's called partial. Now, there's an equivalence here. For every partial FSA, there's a total FSA that accepts and rejects exactly the same string set. It's very easy to construct the total FSA. I'll give you an example of this. So here's our original partial finite-state automaton. You can see that it's partial because in Q0, there's no outgoing transition labeled B, and in Q1, there's no outgoing transition labeled A. So here's how I'm going to create an equivalent total finite-state automaton. I'm going to add a new state right here. Okay. And sometimes this is informally called the sync state. It just sort of exists to have a place for all the transitions that were missing from the partial automaton to go to. And so everything that wasn't originally, all the transitions out of states that were absent for particular input symbols in the partial FSA are present in the total FSA. So this state gets a transition from Q0, which is labeled B, since there was no B outgoing transition in the original partial FSA for Q0, and Q1 can go to Q2 in the new FSA with the transition labeled A. Furthermore, in order for it to be for it to be total, this new state also has to have outgoing arcs for all of the letters in sigma, and so we just have a loop arc that that takes A and B on it. So that's shorthand for two separate transitions. One is Q1 takes A and goes to Q2 takes A and goes to Q2, and Q2 takes B and goes to Q2. And you can see probably pretty graphically and visually, it's easy to eyeball that these are equivalent finite-state automata. They will accept and reject the same strings.